All right, guys, we're back. I got a couple questions here. Will the TD7 indicate whether the unit is currently in a purge cycle? Yes, it should show that we're in a purge cycle. Let me check the other chat window. Okay, I think that was the only one. So, all right. Here we go. So compressor protections, difference between comfort purge and condenser purge. Thank you. I think actually, and I don't have a unit in front of me to verify, I believe when it goes to purge, it's just going to tell you we're in a purge mode. It's not going to differentiate. It's just going to indicate purge, but I'll have to verify that whether it'll actually tell you we're in comfort purge or condenser purge. Okay. Compressor protections. Here's a list of some of basically the diagnostics you're going to see. Low ambient lockout, low compressor suction pressure, loss of charge protection, discharge pressure limit, high saturated suction pressure, high differential pressure protection, coil frost protection, and reheat evap limit. So that's a few of them. There's more out there. We're going to try to get into looking at some of the different diagnostics basically, and this is what happened, and this is how the unit is going to try to prevent these things from happening. So when we're looking at these compressors, we have this operating envelope. If we're inside this envelope, the compressor's happy. And when we start getting outside the envelope, we run into issues where the compressor, we can get a failure, high pressure trips, low pressure trips, loss of charge. And so the unit is going to do a lot of internal calculations because now the controller itself can see what the discharge pressure actually is. We can see what the suction pressure actually is. We can see what these temperatures are throughout the unit. And so we can actually operate the unit and try to prevent some of these trips. And a lot of the logic we're going to look at, if you're used to working with CGAM, it's going to be very similar to what that CGAM protection is. The thing is, we're looking at it from a standpoint of if the unit's running and we're approaching a trip point, if we can back off the unit, some cooling is better than none at all. Because if we trip, it's off. So a lot of the logic that they built in here is going to try to prevent the unit from going into a manual lockout diagnostic. A couple terminology, stuff that we're going to look at, some of the stuff we're going to talk about. With double swap, we talked about double swap before. The unit will swap compressors on a circuit to change capacity of that circuit. Stage off a 10 and bring on a 15. Stage off the 15, bring on the 10. Sometimes when we're in a limit situation, we can still do a double swap and it's still allowed. And it's not counted as actually adding capacity, it's counted as a double swap. So load, when we're in a load situation, circuits in normal operating, we're able to stage compressors up and down as needed. There's no restrictions in any way, shape, or form. When we're in a hold mode, then that circuit will come up as saying being held by certain diagnostic, held by high pressure or something along those lines. The circuit will hold at its current state. So we're not going to add capacity. We're able to stage capacity down if we need to, but we can't add any capacity. Double swaps when we're in a hold is still allowed as long as the end result is going to be lower capacity. So we got a 15-ton compressor running and we're in a hold, we can stage down to the 10 if we need to, but we can't add the 10. Unload region, so when we're up in an unload area, then whatever compressors we have running, we're approaching a trip point, we're actually going to start unloading it, even if it means that we're not meeting the demand. even if it means that we're not able to provide the discharge air temperature we're trying to do. We're trying to back the unit off in order to keep it online. So low ambient lockout. Fixed speed condenser fan motors, typically 45 to 55 degrees. Actually, there's one unit there that gets up, actually has a low ambient lockout of 70 degrees. It's probably more along the lines of a process system where we're entering the air conditions are going to be upwards of 90 plus degrees. So that low ambient lockout we said was on page 77 in the IOM. Variable speed condenser fan motors. Now we're doing low ambient. That without hot gas bypass, we're looking at 0 degrees. And with hot gas bypass, we're looking at 10 degrees. Okay. So if we are in a low ambient situation and we need to start the unit, but we're not quite below that low ambient lockout point, we look at what the low pressure cutout is going to be, and it's a pressure that we have set up in there. 1.5 times the low pressure cutout and the circuit is inactive, then if we're less than that, then no compressor on that circuit is going to be allowed to start. If we have fixed speed compressors, our low pressure cutout is going to be 22 PSI 22 PSIA. So 1.25 times 22 PSIA. If that suction pressure transducer on fixed speed compressors reads less than 27.5 PSIA or roughly 13 PSIG, we're not going to start a compressor. Pressures are too low. For variable speed, that pressure goes up. Our low pressure cutout is 36.5. So we're looking at if that suction pressure transducer reads less than 31 PSIG, we're not going to bring a compressor on. For low pressure cutout, there's those settings for before a compressor starts. If that transducer is reading for fixed speed 22 PSIA, then we're locked out on a low pressure cutout. After that compressor starts, that number goes up to 36.5. Okay, so compressor starts after 5 minutes, we're going to raise that pressure up. We have variable speed compressors, that pressure is higher. And we're looking for basically low ambient situation or loss of charge situation. So variable speed compressors, we're looking at 36.5 before the compressors start. And after starting, we're looking at 40.8. Low pressure. Oh, hold on one second.
So back to the balanced wear thing, that's going to be under settings. And it's under feature settings to enable, disable balanced wear. I had to reconfigure my panel. Fine. I have to reconfigure it again now to go check for that hot gas bypass set.
We can't have balanced wear and hot gas bypass.
Right.
Right. So low suction pressure limit. So on startup, the low pressure cutout will be based on the lower setting. That less than 20 low pressure cutout stays at the lower set point for 170 seconds. Greater than 40 degrees, low pressure cutout stays at the lower set point for no time. On startup, we're looking at that 7 or 22. So when the compressor first starts, depending on the outside ambient temperature, if we're less than 20 degrees outside, we're going to keep looking at that 7 or 22 PSIA as our low pressure cutout for 170 seconds. If it's above 40 degrees outside, as soon as that compressor starts, we're going up to that 22 PSI. And it's going to be linear in between. So when we're between 40 and 20 degrees, that number is going to float. So low suction pressure limit. So applies to multiple compressor circuits only. So we have to have multiple compressors. Where if we have a variable speed compressor by itself, it's not going to apply to that one. But if we have variable speed with a tandem or a fixed speed compressor with it, then it will. while the circuit is running, if the suction pressure drops to 1.4 times that low pressure cutout setting we were looking at, we're not going to allow any other compressors to start. We're not going to unload anything, but we're going to be in a hold situation. We're not going to let any more compressors start. So as that suction pressure starts to go down, we're going to try to hold those compressors and keep from going into that low pressure trip. Loss of charge protection. So we're going to look at suction pressure, discharge pressure, suction line temperature, entering evap temp sensor, as well as EXV percentage. And internally, it's going to do some calculations, and it's going to calculate if we have a low charge or a loss of charge. So we will look at the calculation, and if it stays too low for more than 5 minutes, then we're going to lock that circuit out and count that as a loss of charge diagnostic. If we have hot gas bypass, if we have hot gas reheat, and those are active, then we're not going to look at this. So we have two calculations that we generate on loss of charge. There's two settings in there. The first setting is going to be that X percentage. It's a higher percentage. If we are approaching that loss of charge set point, then you're going to get a warning diagnostic. We're not going to shed compressors or anything like that, but we are going to give you an informational warning saying, hey, we're approaching that loss of charge. We've got a loss of charge detected. If we drop below that for 5 minutes, then you get your manual lockout.
Question here. Are we relying solely on pressure transducer or high and low cutout settings? Are there separate? Low pressure, that's...
Low pressure, we're looking strictly at the suction line pressure transducer. For high pressure, we also have a high pressure cutout that can trip the unit off. Your safety.
Last chance kind of thing.
Right. High pressure protections. We're looking at the high pressure cutout. We're looking at high saturated condenser temperatures. We're looking at high saturated suction pressure, and we're looking at high differential compressor pressure. So, compressor discharge pressure limit. The high pressure cutout is 675 psi or 660 psi. That is the compressor trip point. Once that pressure gets up to there, that high pressure cutout will open. We drop the unit out, as well as looking at that pressure transducer as well. We're looking at that, it's counted as a trip. So we shut off all the compressors on that circuit. Initiate a high pressure diagnostic and lock it out. Since we have a transducer though, as that pressure starts to go up, if we get to 97% of that high pressure cutout, so high pressure cutout 660, we approach 640 when we get above 640, but before we get to 660, we go into an unload region. If we have 2 or more compressors running, we start to unload compressors trying to drop that pressure down. If there's only one compressor running, then we hold that compressor where it's at. We do not allow to add any more capacity. Once that pressure drops back out of that unload region, you start a 60-minute hold timer. A lot of timers we start in this thing. If we are running and we're approaching 85% of that high pressure cutout, then the unit goes into a hold state. If we were here at 97 and we shed a compressor and it dropped us down to here, then we have that 60-minute timer running as well. So we're going to hold the compressors at a current state. We're not going to allow to add any more compressors. We can shed compressors if we need to. We can do a double swap as long as the total capacity decreases. Once we're below 85% of that high pressure cutout, we're back to normal operation. We can add compressors, take away compressors. If we had started the timer because we were in that unload region, then before we're allowed to add compressors, we have to wait for that 60-minute timer to finish expire. So basically we're looking at some cooling's better than no cooling at all. And this is a per circuit diagnostic. It's not for the entire machine because we have a transducer we're looking at on each circuit. High saturated discharge temperature. We only use this on variable speed compressors. We calculate it using the discharge pressure, and it's used to keep us from loading up more compressors on that circuit when the pressures or temperatures are too high up. It's internal calculation. A lot of these settings can't be changed, they're fixed. So high saturated suction pressure. Now instead of looking at discharge pressure, we're looking at suction pressure. We're looking at used on variable speed compressors. They do an internal calculation looking at suction pressure. Used to shut off compressors, including the variable speed compressor. If we need to, we can back it off and then eventually shut it off if the suction temperature gets too high. So if that temperature gets too high up there, we run the risk of suction gas going back, being too warm, overheating a compressor and running into problems. So we will back off. High differential protection. So what we're really looking at here is this green section in the compressor. And so we don't actually have any temperature sensors or pressure sensors in there, so we can't really look at that internal area. So the unit is going to look at discharge pressure and suction pressure and some temperatures, and it's going to do an internal calculation to figure out what that envelope pressure actually is. If it gets too high, then we run into the issue we may damage this internal scroll, whether the tip seals or we fragment that scroll up. So it's a protection situation going on. It's doing internal calculations to try to prevent that from happening. So it's based on the unit size, the capacity, and the current performance that we're doing. So now we get some weird graphs. For fixed speed compressors, that high compressor envelope differential pressure, as long as we stay down in this section here in this green area, it's okay. We can add and subtract capacity all day long and we're okay. If we get up into this yellow region here, that's that hold region. Don't add capacity, but we can maintain where we're at. Once we get up into this red section, now we're looking at unloading compressors and trying to back everything off. And we're going to start our timer. So, in the high differential protection, if we climb up here into the unload region, we start a timer. We drop back down, we unload compressors. Once we're allowed to start compressors again, we have to satisfy this timer. High differential protection timer is going to be a 10-minute timer. Variable speed compressors, we're still doing the same thing, only we're able to modulate the speed of that compressor. So if we need to, we can back it off. Get up into the hold region, we're not going to add capacity. We get up into the unload region, we're going to start backing that VFD off, slowing that compressor back down. All right, coil frost protection. We're looking at suction line temp. We have that suction line temp sensor. If it drops below the frost protection set point, then the unit goes into frost protection mode. So coil frost protection will be calculated per circuit. It's an adjustable point. When the outside air temperature is above 65, we're going to ignore it for 30 seconds. If it's below 0 degrees, basically, we're going to ignore it for 5 minutes. It's going to be that linear scale in between there. And it's basically keeping that coil from frosting up. It's not going to be a manual lockout. When everything warms up, we'll allow everything to start back up again. So basically disabled whenever we're in dehumidification, when we're doing any of the purge cycles. Okay. So your set point is basically your coil frost threshold, which is that 28 degrees. It is an adjustable point. And then we have a delta T that we add into it, or that the unit adds into it. So we'll add those two. If that suction line temp sensor gets down to 36 or below, we're going to hold where we're at. Try to prevent going into that frost protection. If it drops below that threshold, that 28 degrees, then we're going to back off compressors and allow that saturated temperature to rise back up. Basically, if we drop below the 28, we're gonna start a timer. If we stay below there for 60 degree seconds, we're gonna back off a compressor, and then we're gonna start that calculation again for 60 degree seconds. And if we need to, we'll back off other compressors. So, and that's basically what this is. Yeah. So saturated suction temperature remain below the threshold for 28 degrees there, and there's only one compressor on. So now we've backed off to a single compressor. The next time it unloads that last compressor, you'll get a diagnostic. It'll be a frost protection limit. And now we're actually backed out all the way, and that is an auto reset diagnostic. It'll sit off until that circuit, that saturated suction temperature, rises above that coil frost threshold, which we said was 28 degrees, plus the coil frost delta, which was 8 degrees. Those are the default set points. So once we get back above 36 degrees, we'll allow the circuit to start back up. Okay. Anytime while we've backed off and unloaded, if at any time we get back above that 36 degrees as well, we'll go ahead and go back into our load application and allow that to start back up.
Sorry, I got pulled out. The one about, can the unload percentage be lowered?
That's back here. Yes. I do believe it is adjustable. I'm gonna have to verify that. It's very similar to what we do with CGAM. And so I do believe it is adjustable, but I'm gonna need to verify that. Because I know that, I'm from originally Arizona, and we climb up there frequently. So there's your charts for coil frost protection, saturated suction temp, hold region, unload region. For fixed speed, for variable speed. Superheat high limit, it's used to detect excessive refrigerant loss on a circuit. Units with a single evaporator use the suction temp sensor. Units with split evaporators, we're gonna average those temp sensors. Basically, we're looking at that suction pressure transducer. We're looking at the suction line temp sensor. We're gonna ignore it initially on startup. Should the superheat rise above the set point, depending on where you have it, so 50 to 65 degree delta, then we're gonna lock it out on high superheat, and we're gonna initiate a diagnostic. So we'll lock out that entire circuit. So those are most of the protections internally. A lot of this stuff is internally calculated from the unit, and we're trying to maintain keeping the unit online before we actually get a trip. So any other questions on that? a staggered coil, which coil is circuit 1 or 2, or are they connected to both coils? So when we looked at that, let's come back up here and see if I have a decent enough picture. So if you look at those coils, they are intertwined with both circuits on the staggered coils. We don't have a really good picture of that. It's going to have 2 EXVs on each coil because we have circuit 1 and circuit 2. So they are intertwined together. They're designed to work so that, it doesn't matter which circuit we bring on, we get the entire coil face cold. So that way we can compete instead of having, only part of the coil and not the other part. So they're all intertwined. So there really is no circuit 1, circuit 2 on there. Both circuits are on each coil. Okay. Any other questions on that one? Dig through some windows here. Feel like Zach yesterday, man.
Oh man, dude, the amount of windows open was ridiculous.
All right.
Off the chain. Started or?
Let's see here. We are 8:50. You're the boss. What do you want?
You're the boss today. I worked all day yesterday.
All right. You guys doing okay? Keep going, or you need a quick break? If I hear nothing, then we'll keep going.
Coming up on about halfway through the session.
Yep. Okay. Airside. All right, so we're going to take a look at some of the different fans. Well, there's really only one kind of fan.
Break.
Oh, somebody said break. Yeah, one person with a break.
That's fine. Before we get started, that was a lot.
Yeah.
A little longer one.
All right, boss man says take a break, so we'll start back up at 5 after.
I'm not the boss. He's not.
He likes to think so, but we're gonna rope it.
Lying?
Yeah. All right, let's do a break. Start back up at 5 after.